Having discussed in the last video how to go about measuring standard potentials, let's now take a look at their utility. So let me consider a full electrochemical cell reaction. Right? So I have some standard state free energy of reaction is going to be equal to the standard state free energy of oxidation plus that of reduction, and those are all related to minus NF standard state reduction potential. And so we've worked previously with zinc and copper, so I'll put those two as examples. So here would be a balanced set of two half reactions, balanced because the electrons cancel out on each of the two sides. And so when I sum these two equations together, I get the requisite zinc ions plus copper solid in equilibrium with copper ions and zinc solid, and the overall free energy of reaction is going to be equal to, well, this one is written in reduction mode, and so we do have that the reduction free energy is minus 2 because it's 2 electrons, F standard reduction potential. In the next reaction I've reversed it. I'm actually measuring an oxidation free energy, and so that's going to change the sign. Notice that my minus sign has gone away. That's because I'm still going to look up somewhere a standard reduction potential, but I'm going to change the sign because I'm using the half cell in an oxidation mode. So adding these two together would give me either this or this, depending on whether I'm working in free energies or standard potentials. However, it's impossible to measure either of these two quantities individually. We're not allowed to just go get a bottle of electrons off the shelf and put them into a chemical reaction and measure energy changes. As I mentioned in earlier videos, electron neutrality is an absolute requirement. Actually, I don't know if you've heard this example before, but if you were to take a bottle of electrons, were that to be possible, let's say you took 1 mole of electrons, and if you think about that, 1 mole of electrons weighs very, very, very little, right? Because 1 mole of hydrogen atoms from which you might have taken those electrons would only weigh 1 gram. And the electrons weigh something like 1/3600th, if I remember that from physics, of the hydrogen atom. So it's a tiny, tiny amount. And meanwhile, why don't you take that 1 gram of now protons and put that in a different bottle? And if I had you take those two bottles, the electrons to the north pole of the Earth and the protons to the south pole of the Earth, and just asked you to lift them, why would it be hard to lift them? Well, it wouldn't be gravity, because we've already established that one bottle weighs 1 gram and the other weighs a lot less than 1 gram. But you would be unable to lift them because the force attracting them from having taken those two charges, two sets of charges, moles worth of charges, and separated them, even by the radius of the Earth, is something on the order, and I didn't look it up before I did this video, but it's on the order of tons, as I recall. So extremely difficult to separate charge. We can't do it. Instead, coming all the way back to thermodynamics, we adopt a convention. And our convention is we're going to pick one half cell, and we are going to arbitrarily assign the standard reduction potential for that cell to be 0. And then we'll determine all other potentials as a potential relative to that cell. So what is the cell that's chosen? It is the so-called standard, because we are standardizing our scale to it, standard hydrogen electrode, sometimes also abbreviated SHE, and it is the half cell corresponding to protons at unit activity in aqueous solution being reduced to hydrogen gas at 1 bar pressure. So the standard reduction potential for that half cell is defined to be 0. So with that in mind, here I have just rewritten that. Now I can create an electrochemical cell and measure its E0. And in the last video, we saw how to use Debye-Huckel theory to actually create a cell with varying concentrations and extrapolate it back in order to get the standard state potential. And now I think about this full cell as having come from, well, here's the hydrogen electrode hiding in here. It's actually reversed, right? The hydrogen is being oxidized, but that's okay because if the reduction potential is 0, then the oxidation potential is -0, and that's still 0. So by convention, I have that oxidation potential is the minus the reduction potential, it's 0. And as a result, since these two must sum to 0.222 volts, it must be the case that the reduction potential for this half reaction, silver chloride plus an electron, goes to chloride plus solid silver, has the potential, standard potential, 0.222 volts. So given that we've got one electrode set, we can really determine all the others in this way. Pretty much any chemical reaction you can imagine, you'll ultimately be able to bootstrap your way back to the hydrogen electrode reacting with something. Now maybe I could take this reaction and add another half reaction that will give me yet another possible cell. And in the end, I can tabulate a very large number of standard reduction potentials. Those standard potentials will be either positive or negative numbers. And the sign of those numbers is just telling you relative to the hydrogen half cell, which defines 0, is it more or less favorable to do the reduction, excuse me. And so a positive reduction potential, remember, is a negative delta G. So positive standard potentials, since they are more positive than the hydrogen electrode, it is delta G negative, more favorable to reduce them, and vice versa for negative potentials. So here's an opportunity to play with that with a particularly relevant reaction, which we'll spend a little more time with later. And what's shown here is called water splitting. So we are taking 2 moles of water, splitting them into 2 moles of hydrogen gas and 1 mole of oxygen gas. And the standard state free energy of reaction for that process is 474.3 kilojoules per mole, as written. So if you like, it's per mole of oxygen. And so the question to work on for the self-assessment is, what is the standard reduction potential for this half cell reaction? Oxygen gas plus 4 protons plus 4 electrons goes to 2 liquid water molecules. So I'll spend a moment on this self-assessment just because it is a pretty important one. And let's think about how to go about solving that. So I know the standard state free energy of reaction, and so I know the standard cell potential. So I will take minus that free energy, 474, and I can't explain why this says 3 and that says 7. That's an interesting little misprint, but we'll work with less than 1% error. Minus 1 over n times this value, divided by the Faraday constant. And what is n? Well, in this instance, n is 4 electrons. So that was for the equation as written and given with this free energy of reaction. But I want to reverse it because what I've been assigned to determine is this half reaction, O2 appearing on the left-hand side. So I need my O2 on the left-hand side. In order to balance the electrons, I've got 2 hydrogen gas molecules over here. They are being oxidized to 4 protons and 4 electrons. Remember, by convention, this is just the standard hydrogen electrode again. That is 0 volts. This is 4.92 volts divided by 4 electrons is 1.23 volts. And in order then to have this plus this equal this, the standard reduction potential for this reaction must be 1.23 volts. So reaction of oxygen with protons and electrons to make water. Here in fabulously small font is a promised tabulation. I told you it's good to have tables of these values. Tabulation of standard reduction potentials. So you see this little curly E with a superscript 0. So there's the standard reduction potential in volts. Sure enough, here outlined at 0 is the standard hydrogen electrode. So by convention, it's chosen to be 0. The problem we just worked out is actually also on here. O2 plus 4H plus 4 electrons goes to 2 water. And sure enough, we did it right. It's 1.23 volts. And looking at some of these potentials, you should also notice I said as a potential is more positive than the standard hydrogen electrode, it shows a greater propensity to be reduced. So here we have fluorine. The most positive potential is fluorine gas. ripping electrons from anything it can, but in this case, if you were to rip them from hydrogen, it would happen with 2.87 volts of driving force per electron. Similarly, if we go to the other end of the standard potential table, we see alkali metals, which for the most part are uninterested in their own electrons. So lithium cation, you can add an electron to it to make lithium metal, but compared to the standard hydrogen electrode, lithium's not that interested in that electron. So minus 3.05 volts is the standard potential in that case. So, and there are many, many other examples in here, some of which we've seen before: copper, zinc, silver chloride, and so forth. So next, we are going to take a look at how electrochemistry and these standard potentials can be used to determine other thermodynamic properties of interest.